Discuss one more topic based on Kirchoff's law itself. Kirchoff's laws, we have studied two laws. So the first rule is the current rule, that means the junction rule, and it is based on the law of conservation of charge. The second rule is the loop rule, and it is based on the law of conservation of energy. So you can expect a question for your boards like this: how will you justify the Kirchoff's both laws? Okay, so how will you justify the laws? Current rule can be justified like this. That rule is based on the law of conservation of charge, and the loop rule is justified in this way. It is based on the law of conservation of energy. Okay, so this is the justification for Kirchoff's laws. So children, let's discuss some of the numericals based on Kirchoff's rules. So we had studied two rules of Kirchoff. That is, the total current at a junction will be equal to 0. That means total current entering in a junction is equal to total current leaving the junction. This is the first rule. And which is the second rule? The algebraic sum of the change in potential in any closed loop will be equal to 0. So the second rule is the loop rule, and it is applicable only to a closed loop. Okay. So on the board you can see a circuit, and you need to solve the circuit using the Kirchoff's rules, and you are supposed to find out the value of current I2 in this circuit. And here there are two loops. Let this be our first loop and let this be our second loop, and we can move through the loop in any direction. We can follow either clockwise direction or anti-clockwise direction. For now I have opted the anti-clockwise direction. That means we need to move through the loop like this, through each loop. Okay, you can also follow the clockwise direction, no problem is there. But before moving to the numerical part, you must be aware of some of the tricks that will be helpful for you to solve these problems. So this is the trick number 1. See, if you are moving through the loop in this direction, and while moving through the loop, you are moving from positive to negative terminal of the cell, that means this cell, then we can consider the potential as negative. So if we are moving from positive to negative, then 40 volt can be considered as minus 40 volt, because you are moving from positive to in this direction. But at the same time, if we are moving through the loop in this direction from negative to positive, you can consider 40 volt as plus 40 volt. Okay, so that is the trick. Here if you are moving in this direction, that means from negative to positive, you can consider, or you can take the potential value as positive, or the EMF value of that cell as positive. And next trick is that suppose you are moving in this way, and the current is also flowing along the same direction. Then the potential drop across this resistor, that is IR, can be considered as minus IR. So the potential drop IR can be considered as minus IR if the current and the direction of the current and our direction is same. Okay. And next, the fourth rule is that suppose we are moving through the loop in this direction, but current is flowing in the opposite direction. In such cases, the potential drop through this resistor R, IR, can be considered as plus IR. So the potential drop IR will be considered as positive if the direction of current and if our direction is same. So these are some of the tricks which will be helpful for you to solve these problems. Now we can start. So first, let's apply the Kirchoff's voltage rule or the loop rule to the first loop, and through the first loop we follow in this direction. So let this be the direction of loop A, B, E, F, A. Okay, we start from A, go through B, E, F, A. So this is our loop, and we move in this anti-clockwise direction. As we move from A to B, there are no any components, so there won't be any voltage drop. As we move from B to E, there is a resistor 40 ohm. And what is the current flowing through the resistor? I1. I3. I3 is the current flowing through 40 ohm. So when current flows through resistor, there will be a potential drop. And what will be the potential drop? It will be IR. That means I3 into, what is the resistance? 40. So the potential drop here will be 40 into I3. Then what should be the sign? We are coming in this direction, but current is coming in the opposite direction. So IR can be taken as positive. So this is positive itself. Then what is the next component here? It is a cell, and we are moving from positive to negative of the cell. So whenever, as per the first trick, whenever we move from positive to negative of the cell, we can consider that EMF of the cell as negative. So it will be minus 40. Then no need to write the sign. Then again, as we move from E to F, there are no components, so there won't be any potential drop. Then as we move from F to A, there is a resistor, and the current flowing through that resistor is I1. I1 is the current flowing through that resistor. Okay, so we are moving in this direction, but current I1 is coming in the opposite direction. So the potential drop across this resistor can be considered as positive as per the fourth rule. So that potential drop is plus, and what is the current? I1, and what is the resistance? 20. So 20 into I1. And as per the Kirchoff's loop rule, the algebraic sum of this potential through the loop 1, closed loop 1, is equal to 0. And we can just rearrange this expression. We can just rearrange this expression like this. It can be written as 20 I1 plus 40 I3 equal to 40. Okay, we have just kept all the I1 and I3 terms on the LHS, and we have just changed the constant terms to the RHS part. Again, we can simplify this expression. Just divide all the terms by 20. So you will get I1 plus 2I3 equal to 2. Okay, so this is our first equation, and let this be our equation number 1. Now let's try to solve the second loop in a similar way. So whenever you solve the second loop, you need to follow the same anti-clockwise direction. And which is the loop? It is B, C, D, E, B. Okay, B, C, D, E, B. This is our loop. Now, as we move from B to C, no components are there, so no potential drop. As we move from C to D, two components will come. First is its cell, and we are moving from negative to positive of the cell. So as per the second trick, when we move from negative to positive of the cell, we can take the potential or EMF of the cell as positive. So here the EMF can be considered as 80. Okay, 80. Then what is the next component? It's a resistor, and current I2 is flowing through 20. We are moving in this way. Current I2 is also flowing in the same direction. So the potential drop can be considered as negative. So it is minus I2 into 20. That is 20 I2. Then again, as we move from D to E, there are no components, so no potential drop. As we move from E to B, first we come across 40 volt, and we are moving from negative to positive of the cell. So the potential is plus, so plus 40. Then again, another component is that 40 ohm, and the current I3 is flowing through 40 ohm. We are moving in this direction. Current I3 is also flowing along the same way. So we can consider the potential drop across 40 now as minus. So we can take minus 40 I3. So this is the algebraic sum of the change in potential through the closed loop 2, and the algebraic sum will be 0 as per the Kirchoff's loop rule. Again, we can rearrange this. We can just write like this. It is minus 20 I2 minus 40 I3 equal to 80 plus 40 is 120. When we take it to the next side or RHS side, it will become minus 120. Right? And again, we can just rearrange this. We can just divide all the terms by now. Here there is a problem. See, first we got an expression. When we solved the first loop, we got an expression like this: I1 plus 2 I3 equal to 2. So the variables here are I1 and I3. But when we solve the second loop, we got the expression involving I2 and I3. Here we have I1 and I3. Here we have I2 and I3. So I3 is common in both the expression. Here we have I1, here we have I2. So we need to change this I2. Okay, so that we could get an expression in I1 and I3 alone. So how can we change I2? For that we need to use our junction rule. Which is the junction rule? The total current entering in the junction is equal to total current leaving the junction. So if you consider which are the three currents here, the three currents are I1, I2 and I3, right? So when we consider this junction B, I1 and I2 currents are leaving the junction, but at the same time the current I3, this is the current I3 is entering into the junction. So can we write like this? The current I3, that is current entering the junction, is equal to the total current leaving the junction, which is the total current leaving the junction I1 plus I2. So we can write I3 is equal to I1 plus I2. From this what will be I2? I2 is equal to I3 minus I1. So we got an expression for I2 here. So just write minus 20 into I2 is, yes, I3 minus I1 minus 40 I3 equal to minus 120. First we can just omit this negative sign. Negative on each term we have negative, so it can be cancelled. Then we will get 20 I3 minus I1, 40 I3 equal to plus 120. Remove the bracket. When you remove the bracket, you will get 20 I3 minus 20 I1 plus 40 I3 equal to 120. Right? Now 20 I3 plus 40 I3, it is 60 I3 minus 20 I1 equal to 120. Now just divide all the terms by 20. So you will get 3 I3 minus I1 equal to 6. Okay, so this is our second equation. Children, be ready with your pen and paper. Okay, just follow along with me. Now we got two expressions, which is the first expression I1 plus 2 I3 equal to 2 and 3 I3 minus I1 is equal to 6. So I am going to rub all these things and let me just start in a new way. We need to solve these two equations 1 and 2 so that we could get the value of I2. Okay. So these are the two equations that we got when we solved the two loops. Now we need to solve this equations. You are familiar with this method in your math. So let's rewrite the second equation. So first we can write I1 plus 2 I3 equal to 2. Then rewrite the second equation. Let it be minus I1 plus 3 I3 equal to 6. Then we need to eliminate this I1 because both the coefficients of both I1 are same. So just add these two equations. Okay, add equation 1 and 2. When you add equation 1 and 2, you will get 0 here plus 5 I3 equal to 8 and therefore I3 equal to 8 by 5 ampere. And what is 8 by 5? 8 by 5 is 1.6 ampere. This is I3. Once you get I3, you can easily find out I1 by just substituting in any one of the equation. Let me substitute the value of I3 in equation number 1. So we will get I1 plus 2 into I3. Instead of decimal, we can just substitute 8 by 5. For I3, 8 by 5 is equal to 2. So I1 is equal to 2 minus 2 into 8 by 5. What is 2 into 8 by 5? It is 16 by 5. 2 minus 16 by 5, that is 10 minus 16 by 5, that is minus 6 by 5 ampere. Okay, and what is this minus 6 by 5? Minus 6 by 5 is minus 1.2 ampere. Okay, so this is the value of I1, this is the value of I3, but we need to calculate I2. So what is I2? When you applied the junction rule, you got I2 is equal to, what is I2? I2 is equal to I3 minus I1. So just substitute here. I2 is equal to I3 minus I1. And what is I3? I3 is 1.6 minus what is I1? I1 is 1.2. So you will get I2 is equal to 1.6 minus 1.2. And again there is a problem. 1.2 is a negative value. See here we got minus 6 by 5. Minus 6 by 5 is minus 1.2. So here we will have I3 minus I1. So 1.6 minus of 1.2. Right? So 1.6 minus of 1.2 is 1.6 plus 1.2. What is 1.6 plus 1.2? It is 2.8 ampere. Okay, so which is the value of I2? Value of I2 is 2.8 ampere. So we have solved this circuit and we found out the value of I2. Children, you need to solve such similar numericals. Okay, I will give you two examples. Please try to solve that. Just do it as a homework, and also you can expect this for your test paper too. Okay. Now this is the homework that I had told you while discussing the Kirchoff's laws. So children, with this I am concluding my session. Notes have been uploaded. Please go through the notes. Do the test seriously. We will meet in the next session. Till then, take care, stay home, stay safe. Thank you.